Let's get to topic 23. Okay, so topic 23, as you will see, is now we're getting into the task of, okay, how to choose a sample size. Okay, we've been talking about the effects of sample size in terms of the standard deviation, right? The variability, the standard deviation of the sample means. So now let's think about how to choose the sample size if you have particular tasks at hand that you're trying to achieve. Okay, so to get us started, let's do a quick review, okay, of confidence intervals. And we talked about it multiple times before, okay, but now reviewing it just to put into the context of why in some cases you want to choose sample sizes, okay? So let me put it this way. A lot of times, I guess the exercise or examples are given to you, right? Like you're given a particular sample size and you're supposed to work with that sample size and go about it, okay? But sometimes, especially I think in study design, so imagine that, well, imagine we are, let's just say, survey designer, okay? Like, let's just say that we want to design a particular survey and then we finally finish designing it and then we need to figure out how many copies of the survey we should send out, okay? So that's actually an example of how to select a sample size that can achieve what you want to do. Okay, so a lot of times, well, as you know now, the sample size plays an important role in terms of how we are able to come up with our, I don't know, in this case, let's say the hypothesis you want to test for, or like yeah, let's just say the hypothesis you want to test for, and then the sample size can play a role because if you're doing a hypothesis, let's just say for the sample mean and stuff like that. And just as we know from the central limit theorem, right? Like depending on the sample size, the standard deviation of sample mean is going to be different, okay? It's the effect of the standard deviation of the population divided by the square root of the sample size, okay? So the sample size plays a role, okay? So sometimes depending on the goals of how, what kind of goals you have in your analysis, you need to determine the sample size, okay? So that's why we're talking about how to choose the sample size. And then the first recall or refreshing memory is about the confidence interval, okay? Because let me put it this way, a lot of times people might want to come up with a confidence interval within certain range, okay? And then that will be the case that, well, because confidence interval, remember, is also related to the standard deviation, right? Of how you are dealing with your sample means. So, okay, without further ado, let's maybe do a review about what we have known already. And let's see how we can link it to what we're trying to do here. Okay, so this is the approximate distribution of sample average, okay, of a particular sample size n. Okay, so you notice here, this is a nicely looking normal distribution, okay, centered at the population mean, okay, with standard deviation of the population standard deviation divided by the square root of n. Okay, so that's exactly what we know by the central limit theorem. Okay, so if I am able to graph it out for the distribution, again, it's the sample average. Okay, we're talking about the distribution of sample average, then we know that it's centered at the population average with standard deviation of the population standard deviation divided by square root of n. All right, so if I want to think about a 95% confidence and then related to that confidence intervals, okay, so on the graph, essentially what I'm doing, as you can see, is that for about, because for about 95% of all of the samples, the sample average and the population average will be within 2 standard deviations away from each other, okay, because of that, okay. Then if I think about the like the average, like the range that I'm working with, okay, I know the distribution of the sample average is this curve, this normal curve that we're seeing over here, okay? Center at the population average with standard deviation by population ST divided by square root of n, okay? And then of course we could compute that, right? If we are given the population standard deviation, we know the sample size, or maybe we don't know, but we try to solve it given other constraint. But regardless, we have this relationship, right? We have the standard deviation of the this particular distance that we're talking about. It is the standard deviation of the sample average, which is the population as standard deviation divided by the square root of sample size. Okay, so that 2, maybe you're wondering about where did that 2 come from? This is just like, if you remember the 68, 95, and 99.7 rule, right, about normal. We know that's going to be about 2 standard deviations, okay, for 95%. So that's where that 2 comes from. Okay, but more importantly, I think the takeaway on this slide and the next, we're going to go there in a second, is that the result that we know here based on central limit theorem is that the sample average, okay, and the population average, they're going to be within 2 standard deviations of the sample average away from each other, okay, for 95% of the time. Okay, so again, the standard deviation, this highlighted colored SD that we're talking about is the standard deviation of the sample average. And that's the distance that we're talking about. Okay, again, we still have the population standard deviation, which is usually larger. Okay, remember, you are doing population standard deviation divided by the square root of the sample size. So it's always going to be the standard deviation of the sample size, the sample average will always be smaller than the standard deviation of the population. Okay, so keep in mind, what do we really mean by 2 standard deviations away from each other? Okay, that 2 comes from the fact that it's 95%. And that is because of the 68, 95, and 99.7 rule for normal, okay? But also here, we're talking about a standard deviation of the average as the distance that we are measuring, okay? So now, if we think about constructing a confidence interval, okay, so here we talk about the confidence, the concept itself, okay? And the concept, and now to construct the actual confidence interval, what we're doing, okay? And conceptually, okay, let's walk through this, okay? So for 95% of all of the samples, okay, if you stand at the population average, which is at the middle, as you know, okay, and if you look 2 standard deviations on both sides, okay, you will find the sample average, okay? So that's what we mean if I come back to this slide really quick one more time, okay? For this sentence, the sample average and the population average are within 2 standard deviations away from each other, okay? So like, I guess geographically or like conceptually, spatially, if you think about it, if you stand at the population average and then look 2 standard deviations away on both sides, you will find the sample average, okay? Plus, this kind of distance is symmetric, okay? So that is the same as saying, if you actually stand at the sample average, okay, from a particular sample average that you're able to compute, and then if you look 2 SDs on both sides, you will capture the population average. Okay, so it's a pretty important concept here that we started off, if you remember one more time, okay? Sorry, here. Oops. Oh, sorry, okay, here. Yeah, so if we come back to this slide, what this is saying is that we know the distribution, right, of the sample average, okay? We know that it's going to be centered at the population average, and we know that about 95% of all of the samples, the 2 averages are within 2 SDs from each other, okay? But now imagine how we actually are doing of confidence intervals, okay? If you remember what we did roughly before, and now specifically, if you imagine what you actually going to be doing for a confidence interval is that we only get 1 sample, right? We're trying to, like, we have a sample average, right? We know the distribution of it by central limit theorem, okay? What we're trying to do is to construct a confidence interval around the sample average that will be helping us to determine where the population average is, okay? So let me put it in another way. Like if I look at this graph, okay, I know in theory, my sample average should be centered at the population average, right? But maybe, and in many cases, we actually don't know exactly the population average is going to be. We only know that it's going to be where the sample average is going to center at, right? But we don't know what it is. If you know what it is, we don't even do any kind of inferences anymore, right? You can always just work on the population. You can take the mean, take the standard deviation, everything is done. You don't even need to do inference, okay? It is because we don't have access to the population. We have to do some kind of inferences like what we're doing, okay? And then in specifically, we know from the central limit theorem from this graph that the sample average, the distribution of that going to be centered at the population average, okay? So the task is almost like, oh, I know it's going to be centered at the population average, but unfortunately, I don't know where it is, okay? So in another way to think about the inference that we're doing is that, oh, instead of the unknown population average, what I do know is the sample average that I get from my sample, right? So because of the symmetric of the distance that we're doing over here, okay? If you stand at the population average within 2 standard deviations, you're going to see the sample average, right? Then that is the same as saying if you stand at the sample average, which is what you can get from your sample, and look 2 SDs on both sides, you will capture the population average. Okay? So that's why when we are constructing the interval, what we're doing is that we are centered at this point on the sample average, which is what we know, okay? And then we create a confidence intervals for 95% in this case, like 2 standard deviations lower from the mean and then 2 standard deviations larger around the mean. Then that with that particular interval gives you a 95% confidence interval of the population average, okay? So keep in mind that everything is still built on the central limit theorem, okay? But the central limit theorem, let me say this way, like central limit theorem tells us theoretically where the mean is going to be and what the standard deviation is going to be, okay, for the sample mean, okay? But that's only in theory, right? And then for inference, what we care about is what we can say anything about the unknown parameter that we're trying to estimate, like the unknown, in this case, unknown population mean that you might be curious to. Then in that case, what we're doing is that we're constructing the interval based on the sample average, which is what we know, okay? And then we're able to say certain things about the population average, okay? So to sum up all of the stuff that I talked about just now, is that here on this graph, okay, so approximately a 95% confidence interval for the population average, which is unknown, but you want to make inference about, okay, it's going to be centered at the sample average, okay, and then within 2 standard deviations of the sample average, okay. So that's why in practice, the way they're doing it is that you're going to get your sample average from your sample, right? And you're also gonna get your SD of the sample average from the sample by doing population SD divided by square root sample size, okay? And once you get that, you're able to proceed what we mean by this 95% confidence interval, okay? So this might be a little bit new to some of you, even though we did talk about confidence intervals in the past, but here I think it's in a different setup, okay? In the past is if you remember what we did, we simulate under the null, right? When we're doing hypothesis testing, right? We simulate the test statistic under the null for a large number of times, right? And then we construct, okay, a confidence interval that way. So here we are talking through it more mathematically, right? I mean, of course, in theory, if you have the population, you can resample every time for 10,000 times, right? And then you can get a 95% confidence interval that way. That's totally fine, okay? But if you do not have access to any computing powers, or maybe let me just put it another way, that in the past, how confidence interval is taught in textbook for statistics courses, this is pretty much like the recipe for that, okay? But hopefully now it starts to make more sense to you, like the way that we're doing the simulation, okay, and the way that we're doing now mathematically, they really converge the same thing, okay? They're the same concept, okay? We're using the same concept. In the past, when computer was not widely available, this theorem, central limit theorem, was developed, and then people figured out how to construct confidence interval, how to do hypothesis testing from the mathematical point of view, okay? But just remember, all of the simulation that we did is really similar to replicating in theory, okay? If we are able to do this for a large number of times, all of the results going to follow the theoretical result as well, okay? So maybe try to connect those two. And then for us, we really want to make sure that both make sense, okay? And all right, so then if we come back now to my question at the beginning is in what situation you might choose sample size or determine the sample size, and how you're gonna do it is related to this width of the interval, okay? So the total width, okay, of a 95% confidence interval for the population average going to be 4 times the standard deviation of the sample average, okay, because you have 2, right, lower and then 2 upper, so it's going to be 4 in total. And mathematically, it's going to be 4 times population standard deviation, right, divided by the square root of the sample size, because that whole expression is for the standard deviation of the sample average. Okay, so mathematically, this is what we have, okay? All right, so keep that in mind. And we will come back to that when we start to do a little bit more calculation related to sample size, okay? All right, so here we're gonna continue with sample proportions a little bit because proportions are another important parameters people or like in this case, estimates and then parameters of the population that people care about. Okay, like a lot of times, like say, if you do a survey and then you're asking about, let me see, like marital status, for example. Okay, so it's you might be curious about like among the survey respondents, the proportion of married people. Okay, and then that is like, say, if you get the sample, you take like for that marital status variable, you get the proportion like of choosing married, right, over all of this. So that gives you a proportion. So a lot of times you can use the sample, of course, to make inference about the unknown proportion of the population, okay, if your sample is representative, right? So we want to talk through that as well, because in essence, proportions are averages as well, okay, if you can frame your data in a different way. So just now I was talking about marital status, okay, and in a lot of surveys, I think they probably have 6 different categories, like married, divorced, widowed, and then blah, 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 like so many different, 6 in total. So if you phrase if you use the original way of how the data is coded, then it's not really easy to see the proportion of married as averages. Okay, but if I start to recode my data, like it used to be like a categorical variable with 6 different levels, okay, but if I now only focus on the proportions about married, okay, then I can turn my categorical variable into a binary variable, or Boolean, okay, of married or not married, okay, because every other category can be put into the not married category, okay. So in that case, my proportions start to become averages. So the reason what I mean by that is that, let's just say we have a data in that context, okay, so 10 entries of whether you're married or not, okay, married is 1, okay, not married is 0, okay, so I have 10 entries here, and then out of the 10, I think I have 4 ones, okay, so 4 are married is 0, and then 6 are not married, okay. So if you look at this as the data instead of like the different categories, and then we are recoding it into a binary, what we mean only 0 and 1s over here, then the sum, okay, is 4, which is the number of ones, okay, so the proportion, we know it's 40%, right, by just reading the data stream, okay, but it is really also just the average of, if I take about the sum of 4, right, and divide it by 10, that's the number of observations, so it is the average if I code my data into 0 and 1s. Okay, so with this in mind, all of the stuff that we have learned so far about the means, okay, can be transported into proportions as well. Okay, at the end of the day, we need to know about the mean of the averages, or the I should say in this way, the mean of the proportions, right, the sample proportions, as well as the standard deviation of the sample proportions. Just like in the past, we need to know the mean of the sample averages, right, and the standard deviation of the sample averages. And from there, we know central limit theorem, we know the normal distribution, and then we can do the confidence interval like what we described earlier. Okay, so now for proportions, if we know the mean of the sample proportions, if we also know the standard deviation of the sample proportions, and then the central limit theorem actually kicks in again because proportions are averages. Okay, and then from there, we're able to do the stuff that we know, okay? All right, so lastly, if the population consists of 1s and 0s, okay, yes or no to a particular question, then the population average, remember population average is unknown, okay, but is the parameter of interest. So the population average in this context is the proportion of 1s in the population, okay? And then the sample average is the proportion of 1s in the sample, okay? So again, we're back into the game of using sample average, right? Maybe like construct confidence interval. So we're able to say something about the population average that is unknown, but we're interested in, okay? And then everything, like I said, goes back to central limit theorem, okay? So similar to the confidence intervals that we were talking about earlier for the sample means, okay? Here, if you want to do a 95% confidence interval for the population proportion, you centered yourself, right, at the sample proportion, okay? And then you're going to do -2 times standard deviation plus 2 standard deviation of the sample proportion. Okay, so like I said, the question now becomes, right, like, well, the sample proportion, you probably can get it like 0.4 just from the question earlier, right? Like the 0s and 1s of 10 0s and 1s. But then the natural question, I guess, for many of us will be that, oh, how am I supposed to compute the standard deviation of sample proportion, right? Because sample proportion, like, well, we know that for the standard deviation of sample means is the population standard deviation divided by the square root of the sample size, okay? But now for sample proportion, what can we do, okay? So for us, okay, what we are sharing, just like the central limit theorem as before, okay, is again, the width of the confidence interval going to be 4 times the standard deviation of the population divided by the square root of the sample size. Okay, so this is working in a very similar way as before for the sample means. Okay, and but then of course we need to figure out how to compute the standard deviation of the 0-1 population, which we're going to get into in a second in a demo. Okay, but if we just focus on the width of the confidence interval for now, okay, and we just want to talk it through really quickly. If you think about the interval, which is the width of this expression over here, okay? The narrower the interval, okay, the more accurate your estimate is, okay? If you have the same, right, like let me just say this. We have one confidence interval of length 2, okay? Another one, let's just say 1.5, okay? Both of them are 95% confidence interval, okay? So the first one is wider, right? The second one is narrower. Okay, the narrower, I guess the narrower the interval, the more accurate estimate is because you are more confident. Sorry, it's the same level of confidence, but you have a narrow interval, right? So you know that you have a narrow range, right? The population parameter going to be. Okay, so keep that in mind, okay? And I just want to throw a discussion question here and then put you back in the breakout room just to see if you can come up with some kind of idea going on here. Suppose you want the total width, okay, just like the total width is the expression that I'm showing you up here in the middle slide, okay, to be no more than 3%. How should you choose the sample size? Okay, so don't worry if you cannot find out the actual like value of the sample size that you're choosing. This is more like conceptually to make you think about how we are translating this width, confidence interval width question with the sample size. Okay, so again, this is, let me come back to that. Okay, this is page, let's see, page 11. Okay, page 11 of topic 23. So I'm gonna stop share and stop recording. Okay, all right. So yeah, so coming back to this discussion question, okay, we want the total width of the interval to be no more than 3%. Okay, so clearly, as we know, like just how the question is phrased, I guess, sample size is something you can choose, okay, in a sense that we can determine what we're going to do with the sample size. So, so sample size is something going to determine the width, okay, so I guess if we know the standard deviation of a 0-1 population, if we know that, then if we set this to be small or equal to 3%, right, then we're able to solve what the sample size is. Okay, so this, I guess, at the beginning is a math question. Okay, we set, let's just say 0.03 as which is 3%. Okay, and the left hand side is the maximum total width that we will accept based on that. Okay, the right hand side is the formula for the total width. Okay, so you're able to solve it, and then like I said, you can also just set it as like greater or equal to as the upper bound, right? So then you will solve, in this case, the smallest sample size that you will need to make this happen. Okay, so like I said at this very beginning, this is a mathematical question, okay? And in a sense that if you have a target of the width that you're working with, so again, the narrower the interval, right? The narrower the width, the more accurate your estimate is. And that's related to, like I said, some of the goals when you start, like before you start collecting data, determining how large the sample size you want, okay? So if you have a particular goal, like in this case, the width of the confidence interval, then depending on how you're doing your study itself, the sample size is going to be something you have to choose in order to meet your goal. Okay, so keep in mind, we can do this calculation if we know what the standard deviation of the population is. Okay, and sometimes it's given to you, or if it's given to you, great, you don't even need to worry about it. But if you are not given to it, okay, this is what we want to do for a demo, okay, just to get a sense of the standard deviation of a 0-1 population. Okay. And so the graph is what we're going to replicate in a second in the demo. Okay, but maybe before we go there, just to like pause at the graph a little bit. So this is looking at proportions of ones, okay, which is the proportions of ones of the data, okay. And then this is the standard deviation that we're able to calculate, okay. after you get the proportion of ones. So one thing I want you to notice is that the standard deviation is actually a function, okay, in terms of the proportions of ones. Okay, we're just saying that, well, if you know it, then you're able to do the calculation, okay? But like I said, sometimes you don't know it, so you need to maybe find the worst case scenario, okay? That will give you the most conservative sample size that you need, okay? In this case, the standard deviation of this 0-1 population reaches its maximum of 0.5 at the middle point. Okay, so keep this in mind, and let's go to the this standard deviation of 0-1 demo before we break for today. Okay, and then I will walk you through this particular one more carefully, because this is not based on any particular data. Okay, it's really just based on simulation, and then let's see how we can replicate that graph and what that graph is really telling us. Okay. So here, what we're doing is that, remember, we have like the toy example that we get started here is that let's have a population of 0 and 1s of size 10, okay? And then to create that, well, imagine you are doing an array, right? Like you have if I want 2 1s, okay, then what I do is that I do 1 1, right? And then all of the remaining 8 going to be 0, okay? And the way to do that, as you could imagine, is that if I determine the number of 1s as 2 in this case, then I can append, okay, 2 arrays together. Okay, the first array is the number of 1s, all of them as 1s. So this is probably a new function to many of you, mp.1s, that gives you an array of how many 1s that you want in the parentheses. Okay, and then another similar function here is mp.zeros. Okay, so whatever goes into the parentheses is the number of zeros that you want in your case. Okay, so for us, remember, we're doing 2 1s, so meaning that 10 in total, so 8 going to be zeros, right? And then when we print it out here, it's the first 2 1s and then the remaining 8 are zeros. Okay, so this is like a building block, okay, of how we can actually create a 0-1 population depending on how many 1s you have and how many zeros you have. Okay, with size 10. Okay, we're just doing size 10 for now. Okay. So to get a standard deviation of this population, okay, we can use mp.std, right? And then the 0-1 population that we do is 0.4. It's quite interesting in some sense, right? If you think about it, because we know the mean is 0.4, right? The standard deviation, are they always the same? I guess that will be a natural, oh, sorry, never mind. Let me take that back. I guess here the mean is 0.2. We're not dealing with the previous example anymore. Okay, so so I guess, yeah, it might not be really clear at this point about what the standard deviation of a 0-1 population should be in this case. So let's experiment. Okay, what we're doing here is we wrap this thing, okay, the population of size 10, this example, into a function. Okay, and then the input I'm hoping to get here is the number of 1s. Okay, we want to experiment with that number. Okay, so the totals are going to be 10. Okay, so what that means is that as long as you supply the number of 1s that you want, then we're going to create a population, 0-1 population of the number of 1s that you specified and the remaining to be 0. Okay, and what we return here is the standard deviation of that population. Okay, so we run this function. Okay, and then let's experiment with number of 1s to be all kinds of values in this case. So we have 10 values in total, right? So we can have 0 1s, right? 1 1, 2 1s, 3 1s, up to 10 1s. Okay, so that's what I'm doing a possible ones, like as mp.a range 11. So that goes from 0 to 10. Okay, that is all of the integer values, right? That's possible for me to have how many 1s I have. Okay, and then I put it into a let me just create a new, just to print it out. Put it into a table, data table. Okay. Okay, so here is the number of 1s and then a proportion of 1s. Okay, just to get us started. Okay, and for us, this function that we wrote, SD of 0-1 population, if I pass in, remember, right? If I pass in the number of 1s, this column into it, right? I should be able to return an array of all of the standard deviation of each cases. Okay, and when I do that, if I attach it back to the table, I might be able to see some pattern. Okay, that's what we're trying to figure out, like what would be the range of the standard deviation of this. Okay, so if I do that, okay, so notice what I'm doing, I'm using the apply method. Okay, I'm applying the function that I wrote before to the column of number of 1s. Okay, and then I use the .with method, okay, to turn it back into to add it back to the data frame, to add it back to the data table. So let's see what we have done. Okay, so in addition to the number of ones, the proportion ones, we also have the standard deviation of the proportions of ones. Okay, it's kind of symmetric, as you can see here. Okay, so let's plot it. And plotting it will return us to the plot that I show you in the slide. Okay, so now I guess it hopefully makes more sense why the x-axis here is the proportion of ones. Okay, because that's the one that we're experimenting. Okay, and the standard deviation is the y-axis. Okay, so we're, I guess in this case, interested in that if I have 10 observations of 0 ones, okay, and I could have proportions of ones from 0 to 100%, okay, and then we see that this standard deviation is symmetric, right? It's a curve going up and then reaches its maximum at the middle point. Okay, so what this tells us is that for a for a population of 0 ones of 10 observations, okay, the largest possible standard deviation is 0.5. Okay, the smallest, if you look at it, could be 0, right, for those two cases. And it makes sense because when you have no ones at all, everything is 0, right? The standard deviation is 0. Okay, when you have everything as ones, no standard deviation either, because everything is the same. Okay, so with all that in mind, if we come back here, okay, so this is what it's told, right? That this is what the graph going to be. So the worst case, or the largest possible standard deviation, is 0.5 when you have exactly half of ones and then half of zeros. Okay, and this is actually true if you want to experiment with different number of observations as well. Okay, if you do 20, if you do 40, whatever, it's always going to be at the middle point. Okay, so what this helps us, okay, so I will just wrap up here really quick, okay, is remember, we need to solve our sample size in this way, okay? We know the 4, okay, we know 0.03, that's the width that we want to control, right? And the only missing part, okay, is that standard deviation of the 0-1 population that we just did, okay? So what we just did is we got the worst case, the maximum possible value of that population standard deviation is 0.5. Okay, so then you can do the math and solve the sample size in that way. Okay, we called it the worst case because when you have this 0.5 as its maximum, you're reaching the maximum, right? You're reaching the maximum of the square root of the sample size. Okay, and then meaning that any value, so if you have a particular population that the standard deviation is slightly smaller than 0.5, then that sample size that you calculated with 0.5 is worst case, meaning that you are being a little bit too conservative. Okay, but like I said, the worst case is also saying that because the standard deviation, the maximum of it is 0.5. So as long as you have this particular sample size, then you will be guaranteed that your width will never be exceeding 0.03. Okay, so yeah, I will just wrap up here. So on Thursday, it's going to be some discussion questions with Jason to follow up with what we talked about, but feel free to check out the demo as well as all the stuff that we have talked about, and reach out whenever you have questions. Okay. All right, y'all take care, and I will.
All right. Hello, welcome. We're gonna pick up where we left off last time, and I'm gonna do a quick review of proportions, and then we'll finish up by answering a couple of discussion questions that we didn't get to on Tuesday. So if you recall, one of the types of questions, so kind of the data that we've been looking at before, a lot of the data that we've been looking at up until now is we've been looking at averages, like computing means, computing averages of populations. But a lot of times, the data that we want to find out proportions. The biggest example of that is that for election surveys, like, will you vote for candidate X? And it turns out, right, if you kind of if you ask these yes or no questions, you'll get these binary data, zeros or ones, you know, whether they answer true or false, yes or no. But that collection, that proportion is really just an average from there. So we can use the same techniques that we've learned up until now, computing proportions as well. Okay. And so kind of keeping the same terminology that we've had before. The population average, right? That's usually the unknown quantity. That's the number of people, of ones in the population, like the number of people that would vote yes for a certain candidate. And then again, we'll take a sample of those and we'll get a sample average. That will be the proportion of ones in the sample. And we can do the exact techniques that we've done up until this point. We can take a sample of our population. Once we have our sample of our population, we can run a bunch of simulations, 1,000, 10,000 of them. And due to the central limit theorem, we're going to get a histogram. We're going to get a distribution of those simulations. And they're going to be bell-shaped, bell curve shaped, centered around the median of the sample proportion, right? Because we're running the simulations on our sample. And we can conduct a confidence interval by looking at the standard deviation of the sample proportion, okay? And we learned that we can control the width of this, of the distribution of the histogram of our simulations by how many samples that we take. And this is dictated by our sample size, the square root of our sample size. And so basically, the larger the sample that we get, the more accurate our estimate of the population is going to be. But you can see it's not a linear relationship, right? If we wanted twice the accuracy, we can't just sample 2 times as many people. Because it's a square root, we would have to sample 4 times the population to get a double, a double increase in our accuracy. And it's also dictated by how spread out the actual population is, how varied the population is. And so we can, if we wanted a 95% confidence interval, that is going to be 4 times the standard distribution of the actual population, okay? That's the actual population, the standard distribution of that. And basically the more sample size, the narrower the interval. And so we asked a discussion question, if we wanted the total width of our sample interval to be no more than 3%, how would you choose the sample size? And the answer to that is just basically plugging in this formula here. And so the left-hand side of our equation here, this is going to be our 3%. That's the total width that we're going to accept. And then the right side is just the formula that we looked at on the other page. And so we can use algebra and rearrange, and we can get the sample size is just going to be 4 times the standard distribution of the population divided by the maximum total width that we're gonna want to accept. Okay, and so, but what's the fly in the ointment of this? What is kind of the problem with this calculation? Does anyone kind of does anyone want to kind of venture out a guess of why, what is, as it is now, what is kind of the practical limitations of this equation? What do we know and what don't we know? We know the sample size, or what are we in control over? What are we not in control over, right? We're in control of the sample size. We're in control of the sample size. We're in control of how much, spread, how much width we want. But what is really the unknown here? Somebody wants to venture out or type in the chat.
You don't know the real standard deviation or the real population?
That's right, right? So this is the kind of sticky wicket here. This is the fly in the ointment. We don't know the standard deviation of the population, right? And so what do we do? Well, it turns out that we don't even need to know the standard deviation of the population. And why is because we looked last time on Tuesday, we did this demo and we looked at by varying the proportion of a 0-1 population, right? We looked at 10 and then we varied the proportion of ones and zeros. And it turns out, right, because the population, there's really only two choices here. The maximum standard distribution of the standard deviation, the maximum standard deviation of the population is going to happen when you have a 50-50 split between ones and zeros. And this is independent of, this is the maximum and, holds through for any size of distributions. And so what we can do is, if we don't know the standard deviation of the population, but we do know that its maximum is going to be 0.5. It's never going to be larger than 0.5. And so what we can do is we can kind of, we can use the standard deviation of 0.5 as our upper bound, and we know it's never going to be worse than that. Okay, and so now, instead of actually needing to know the standard deviation of the population, it's going to be at most 5. And so we can just plug that number into our equation from there. And so now we have kind of all the variables that we want. And so now, basically, we can control for whatever width that we want in the sample population. We know the sample size. We know the sample size that we need that we can calculate. Before we kind of go on to our discussion questions, is there any questions about this? Okay, great. All right. So for our first discussion question, what I'm going to do is I'm going to use a 68% confidence interval to estimate population proportion. Okay, and so this is different than the other graph, and in some sense, it's good kind of keeping these things kind of straight, right? So for the previous example here, we were looking at the total width of a 95% confidence interval of the population, right? And so this is where this factor of 4 comes from. This factor of 4. If we want to capture the 95% confidence interval for a population, we're looking at 4 times the standard deviation from there. Okay, so this 4 comes from the fact that we wanted a 95% confidence interval from there. And so kind of what is that saying? What is that saying is that kind of at the end of the day, when we kind of crank through all of this, when we take our population sample, we get our distribution, we look at the histogram, and then we basically have our range. We have our range, and what that's going to say is about if the actual, because remember, the thing that we're getting is an estimate of the population parameter. And so what we're actually saying at the end of the day is that, and we're going to give a range, right? So that is the kind of our confidence interval. And so what we're saying is that through our technique, we believe that the actual population proportion is going to be within this range that we've specified about 95 times out of 100. About 95% of the time, our range is going to capture the actual proportion in the population, right? And so that 95% confidence, right? That comes from this comes from where the 4 of the standard deviation comes from. Okay, and that comes just straight from the central limit theorem, and basically going out 2 standard deviations to the right and 2 standard deviations to the left. Right, and that's going to capture 95%. If we went out 3 standard deviations, that's like 99.7. And if we went out 1 standard deviation to the left, 1 standard deviation to the right, that captures about 68%. Okay, so instead of using a 95% confidence interval, I'm going to use a 68% percent confidence interval, which means at the end of the day, when we come up with our range, that range will our estimate, the range of our estimate will be in the population. The actual that will capture the actual population about 68% of the time. Okay, and so I want the total width of my interval to be no more than 2.5%. So then how large must my random sample be? Okay, so I'm going to send you into the discussion. I'm going to make some breakout rooms from here. All right, and then so it might be helpful to just kind of pull up the slides when you go into your breakout room from there, or just write down the kind of parameters, right? So the parameters are 68% confidence, and then the width is going to be no more than 2.5%. And then so how large must I sample be? Okay, so I'm going to open the rooms and give you a few minutes to work on that.
You did it to the potence of 2.
This part, right? You're talking about this right here?
Yeah.
Yep, that's the Python notation for squaring.
Okay.
Yeah, so we're taking that whole thing and we're squaring that.
Okay, thanks.
And the reason why is because the actual formula itself is this whole thing gives us the square root of the sample size. So what I want to do is I want to square both sides.
Okay.
So if I take the square of sample size, if I take the square of the square root of sample size, that gives me the sample size, and then that gives me this times that from there. So that's where that's coming from, and we can see that in this formula here, right? We took the square root of the sample size, and then we squared both sides. And here's the star 2, right? That's the Python operator for exponent. So that's the equivalent of squaring that from there. Great. Okay. And so again, I had forgot to turn on the recording. So let me just go over that real quick. Again, this 2 comes from the fact that we have the 68% confidence interval. So we want to go out one standard deviation on either side. This 0.05 comes from the standard deviation of the 0-1 population. This is the worst case scenario. And then 0.025 is going to be the interval width. That's the range that we want. And we're taking the square of that because we had the square root of sample size. And that gives us an answer of 1600. Okay. All right. And then so now, next question here is, so this is kind of this example here is really kind of you basically are picking you're picking the sample size to give you the percentage that you want, right? And you know this you see this all the time when we look at kind of polls like presidential polls and all of that stuff. You know, this is where they get like how many people want to vote for candidate X. And then they, you know, and it says like 27%, but then you see down at the bottom, right, where it says plus or minus 3, right? That is coming from, this is coming from the width there, right? That plus or minus 3 is a characteristic of the sample size that they came up with, right? And usually you have to dig down a little deeper, right? Because there's 2 things that are kind of come into play. There's the width of the histogram, the sample histogram, and that is what is being captured in this 2.5%, right? So we're going to get this spread, and we're going to get this range of values. But what's not usually kind of said in that plus or minus is what is the confidence interval for that range? And typically it's going to be 95% for most of these polls. But you should actually go and see what is that, right? Because basically even with a 95% confidence interval, it means that that range, the estimates, the actual population value 1 out of 20 times isn't going to be contained within that range from there. So this is an example of where we wanted a particular accuracy or range of our sample interval where we pick the population. But sometimes, right, you just do a survey, and you got as many as you did. Can we then go back and figure out what that range is from the population? And yeah, obviously. And so so this question, and again, I'll send you out over into the breakout rooms. So here we've decided we're going to get 10,000. We're going to estimate our population of 10,000. And then, so now going back to using the 95% confidence interval, what is, with the chance of 95, what is the estimate to be correct within? And then, so let's figure out what that range is from there. Okay. So let me send you back out into the breakout groups. And while I'm doing that, is there any questions about what we're asking for in this problem here? No? Okay. All right. I will, I'll send you off into the rooms. All right, welcome back. And so even though we're asking a slightly different question, it's still the same computation and still the same formula. It's just a little bit of, we're solving for a different variable in this case. And so in this case, right, we have our sample size, so 10,000, and it's a 95% confidence interval. So we want 4 here. The standard deviation of the population of the 0-1 population is still 0.5. We're taking the worst case scenario. And here we're solving for X. This is going to be our percent. And we're going to take the square of this squared, right? To solve for this, we're just going to take the square root of both sides. So we get 100 equals 2. So I've simplified 4 times 0.5 to give me 2 over X. And then just rearranging to solve for X, we find out that X is 2 over 100 or 2%. Did anyone get anything different? And the correlate to that, do you have any questions about how I got 2% from that? All right, awesome. All right, so that kind of wraps up our discussion of that. And so I'll stop the recording.